Welcome to this video on electromagnetism, and here we're going to talk about electromagnetic induction. In the previous video we looked at a small experiment wherein we had this coil, and this coil was connected to this galvanometer. So you can see this galvanometer, and you can see that as I pass this magnet, the galvanometer shows deflection. So as I move this, there is a deflection. And the reason why this happens is because as I move in, when the magnet is here, there is a flux which is due to this magnet at this area. And as I bring it close, the flux increases. And depending upon how fast I bring it, I have the current which is produced more. If I bring it faster, the current will be more. If I bring it slow, the current will be less. So the way we theoretically interpret this is that when the magnet is here at time t1, there is a flux phi1 associated, and this phi1 is nothing but the B1, which is a magnetic field when this magnet is at this position 1 at this area into the area. And this is nothing but B2 when the magnet is here into the area. So the EMF is given by minus N. N is the number of coils. Change in the magnetic flux divided by the time in which the change happens. So that's what we looked into. Now here you see that you have to move this magnet. So the question is, can we achieve this kind of behavior without the movement of this magnet? And for this, we have a slightly different setup. And the setup is, we have, here you have these two coils. And in the middle of this coil is a core, is an iron core. You can see that in the center of that two coils. And we have this coil connected to a galvanometer, and this coil connected to a battery. So that coil is connected to a battery, right? So once I switch on that battery, let's see the behavior, what happens. So right now there is no current in this coil. So as soon as I switch on this battery, you will see a deflection. Yep, there was a deflection in the galvanometer. And as I switch off the battery, let me increase the voltage. Switch off the battery, there is the deflection. So I'll do this again. On, off, on, off, on, off. So when I switch on, it went left. When I switch off, it went right. So the reason why this happens is can be explained as follows. So you have here, you have this iron core, and here you have as an input, you have some coil. This is Ni turns, and then at the output you have coiled. Now as you connect this to your battery, and then as you connect the switch, so as soon as you switch on the switch, there is a magnetic field, there's a current that is produced like this, and because of this there is a magnetic field lines that is increasing in this direction. So this behavior is now of me bringing in a magnet towards this coil, the secondary coil, which is output coil. So as a field increases, just the same way as I bring in the magnet close to this coil, the field increases, and due to the changing field, there's a changing flux lines in this coil, and that produces a deflection in the galvanometer. Now, after I switch off, switch this off again. When I switch on, this happens. When I switch off, the connection is open, then this current, it changes. It becomes, it is receding. And because of that receding current, the behavior is that there is a magnetic flux which is decreasing in this direction. So the magnetic flux continues to be here, but there is a decrease in the magnetic flux lines. Now, since this coil doesn't like that decrease, it tries to produce current to fight that or counter that, and that produces again a deflection in the other direction of the galvanometer, right? So, this kind of explains the basis of transformers, wherein we say that flux in the input is linked with the flux of the output. A transformer looks like this. So you have the same setup, but slightly different. So here you have, in a transformer, you have a setup like this, a core, and on one end you have a coil, and the other end you have a set of coil. So we say that this is your input coil and this is your output coils. So when you pass an AC current or something, the flux lines are changing. In the core, it oscillates as you pass the AC current, and due to this oscillating flux, you will get an output which is also oscillating because the changing flux produces current in the output. Now, going back into this diagram, just a quick mathematical formulation. We know that the EMF at the output is given by minus N output, the change in the magnetic flux by the time, and that will be equal to minus N0, and the flux is produced due to the current in the input. So that is d by dt. In a solenoid, the flux is given by mu naught Ni, that is a B, Ni, which is the input current. This is the input coils, into area. So this is only for K-12 or 12 standard students. So if you're 10 standard or someone, please discard this. So this is your B, which is due to the solenoid. This is mu naught Ni into the area, which is the area of cross section. This is the area of cross section. So there you go. So you get minus N0, mu 0. Oh, by the way, this is mu 0. This is not mu 0. This is mu, because you have the mu of this material. This is a mu of this material. That will be mu 0, mu r. So the mu of that material into Ni into A into d phi by dt. So this quantity here, this becomes what we call as, of course, a minus sign here. This quantity is what we call as a mutual induction, and we say minus m d phi by dt. So that's how you get it. The EMF in the output would be proportional to the rate of change of flux on the left side. So I hope you enjoyed this video. See you in the next one. Bye.